18.5 is looking more specifically at indicators. Remember, indicators are a color signal to represent a change in pH. And it is nice because it is a simple way for our eyes to register a change for something that we would not necessarily be able to see because there's not going to be any bubbling, gas production, so there's no way for us to see the neutralization. The pH or the color change allows this to occur. Keep in mind, indicators are actually weak acids and or bases depending on what their need is for. Therefore, they do have a generic equation in which can be used. H, In for the acid version of an indicator in solution. This is an undissociated form of our indicator, our acidic indicator. So that's going to have one color depending on the type of indicator it is. It can dissociate into its hydrogen ions and the indicator itself, whatever it happens to be. What we are actually looking for is that indicator, and that is going to be the change in color. So as we add whatever happens to be more acid or base to the situation, we will see the color go either way. You could also represent this using a basic indicator as well. Given this knowledge, we can apply Le Chatelier's principle. So if we increase the concentration of hydrogen ions, we're going to shift the indicator back to the reactant side and color A is going to appear. Because we're increasing hydrogen ions, we're increasing the amount of hydrogen present or the amount of acid present in the situation. As we increase number of hydrogen molecules, you decrease your pH. Vice versa, if you decrease the number of hydrogen ions, the indicator reaction is going to shift towards the product, which is the dissociated form. We get the other color, and because there are fewer hydrogen ions, you get an increase in pH, so on and so forth. And this is specifically for an acidic buffer, but the same thing applies, or the same concept applies to basic buffers. You do have a list of buffers in Table 16 in your packet, and they show you the range in which these buffers work, so you know what color A would be and color B would be, and be able to predict when either are present. How does this indicator change occur? Because the particular indicator we're looking at is an acid, we do have a Ka value. Therefore, we took that previous reaction and put it into a Ka or equilibrium expression. Therefore, we have the hydrogen ions times the concentration of your indicator over the acidic indicator itself. At equilibrium, we would expect the indicator concentrations to equal the acidic version of the indicator. Therefore, at equilibrium, or at the point in which that indicator is used, the Ka of that indicator is equal to the hydrogen ions present. We could change that into the pKa is equal to the pH. So when that Ka is equal to the hydrogen ions, that is called the change point or the end point in which that buffer is working. An addition of a small amount of acid or base will therefore change the shift in equilibrium and therefore change the color in which it's taking place. A change in color is caused. Then we have different indicators have different pKa values, therefore have different pHs of color change. So once you know what kind of acid-base reaction you are working with, strong acid, strong base, weak acid, strong base, whatever that combination is, you need to pick the appropriate indicator to show that the neutralization reaction has occurred. So indicators can be used to signal the equivalence point in titrations, which is why you need to know what kind of reaction you are running. When you're using the equivalence point, you need to make sure the end point for the indicator coincides with the equivalence point, so you can notice a change in the color, and the change in color is at the appropriate time. This is really important if you do not have a pH probe to draw a titration curve out. How do you know what's a proper indicator? or how to pick the proper indicator. You need to determine a combination of the acid bases that you're reacting with. Are they strong acids, strong bases, weak, whatever it happens to be, you need to know that combination. You need to deduce the pH of the salt solution at equivalence. So that goes back to 18.3 of your salt hydrolysis. Are you going to be at 7, above 7, or below 7? So you can pick the proper indicator. Then you need to choose the indicator that is appropriate for the reaction in which you're running. An example, if you have a strong acid and base, your pH equivalence range is going to be anywhere from 3 to 11. Therefore, we can use two indicators. You can use phenolphthalein, which has a pKa value of 9.5, and it has an endpoint value between 8.2 and 10.0. And you can also use methyl orange, which has a pKa value of 3.46 and an endpoint between 3.2 and 4.4. So what happens is you are going to use methyl orange to identify the fact that an acid is present. When that methyl orange changes color between that 3.2 and that 4.4, you are now starting into that point of inflection. That point of inflection is going to continue. And it's going to, once you hit that phenolphthalein, which is colorless, and then it goes to pink between your 8.2 and 10.0, you know you've reached or you've gone past that equivalence point. And so you can keep an eye on what color it is you want to work with depending on what type of acid-base situation you're working with.